Hello and welcome back to part 2 of writing an emulator for bare metal radio firmware. In the previous video we noticed that the firmware code accessed the status register of the clock peripheral and entered an endless loop. In this video we continue to model such peripherals to get our firmware to a correct state. Let's take a look at the clock peripheral documentation. So it says the control system can source the system clock from a range of internal or external oscillators. So there are two oscillators, 64 megahertz and 32 kilohertz low frequency. And in terms of the registers, it only has one instance. Base address is this. Then the registers, mostly control registers, start, stop, event register, and nothing about in and out. Alright, so it appears that the clock peripheral is just like a control panel with one knob to select a clock source and some push buttons to start and stop high and low frequency oscillators. As you will see later in later steps, firmware code will use another peripheral called timer peripheral to access counter or timer functionality. So modeling a clock should be easy for our case. As I mentioned, it's just a simple control panel. Before beginning to write peripheral code, it would be a good idea to organize our modeled peripherals. I created a simple plugin-like system under the core folder in the code repository. Since this concept is not related to the firmware or emulation, I just go ahead and copy-paste the finished code. Let's create the folder. First off, we have a class, register class, basically to model peripheral registers. The name, each register has a name, address, and value. We also have two member functions when dealing with peripherals. For instance, this one, oftentimes you either need to know a value of a certain bit or a range of bits. So it could be a good idea to add these member functions, hence bit and range bits. Then we have a parent class peripheral, which all models peripherals will inherit. It is also said to have a custom meta class, so we can keep track of the instantiated peripheral classes using the meta class is peripheral registry. So each time a class is loaded, if the class name was not the parent class, we will add it to a list of loaded peripherals. Finally, we have this function here, load peripherals. We will call this from the emulator just to iterate through all Python module files inside our peripherals repository, and then dynamically import those. first we define the base address, and then a list of registers that belongs to this peripheral. The offset for this register from the base address, which I believe is 0. Let's double check. Yes, start as 0. Start. Stop is 4, and we also have the event register. Events, high frequency, clock, started, set, so these we have this member function creates dictionaries for so helps us to look up registers by both by name and address. Then we define read and write operations on this peripheral. On read, we just get the requested register value from the provided address. If such definition exists, then we use the unicorn to write memory location at that address. So the value needs to be converted to bytes in little endian. Okay, here so writing to registers could have a special meaning besides setting the register value. For instance, here if the address was equal to let's say register name map here to a start command, so basically address of this, then what we do is we reply back to firmware saying that that's cool, we started your high frequency clock, and we basically we set that event register value to 1. And that's it. You can handle other commands similarly inside this write handler function. Finally, we need to also overwrite this member function to return the peripheral name, which is clock. Alright. We can now redirect the memory read and write operation to this class in the emulator. First, let's load these peripheral classes. function would return a class list for us. Then for each peripheral class, we will instantiate those model classes, and then get name. Let's build a dictionary as well here to save this. Instance. Okay. Now inside the memory access callback, you can check if let's run the emulator again. Good. We only see one read access to this event flag register. Let's rerun it with full logging enabled. Okay, we passed that loop, and we see access to two new peripheral, timer 0 and P0. So basically, again, it seems that these register access are inside a loop. If you search for P0 value in nRF documentation, you'll find out that it's actually an instance of the GPIO peripheral, general purpose IO P0 at this address, and these are the list of registers. We have value 8000 X written to outset, and the outset register sets individual bits in GPIO port. So this most probably is an attempt by firmware to turn some element on the board on or off. Later on we will find this out, exactly which element is this. And then in terms of the timer, we have value 1 written to tasks capture register, task capture 0. And this is the timer counter peripheral. Is a general purpose timer to keep track of time in user selective time intervals. You operate in two modes, timer and counter. The block diagram shows 4 commands: start, stop, clear, and that capture in this is command. Let's see, it also has 5 instances. We are using instance 0, or firmware uses that. And task capture 0, capture time value to CC0 register, and the CC0 register capture or compare register 0. Alright, this makes sense. It appears that firmware does not have direct access to the counter or timer value. Instead, when it wants to write or when it wants to read or compare the current value of the timer or counter, it sends a capture command. The command picks that value, puts it in the CC register, where the firmware would be able to read the value. And this is what we see here: capture command followed by a read access to CC0. And most probably this value right here is going to be compared, and because it's not the value that firmware expect, we are again got stuck in a loop. Now let's take a look at the code that accesses timer 0 and P0 to make sense of what firmware was trying to do. I have added the firmware binary with symbols. The Kale compiler generates this as AXF files. This will speed up the code investigation here. We have write access to GPIO at 208C. 208C. Okay, with the help of the symbols, we see it's inside the radio test LED on. The name implies what it's doing. So basically, with this simple command, writing to this GPIO register, this value 8000, it will turn on the LED that is connected to pin 15. Then it reads, does radio test timer read, and returns. Let's see, timer. The write to task capture happens at 2048. 2048, which is part of radio test timer read. It simply writes 1 to task capture and then reads from the CC0. That's all, as we expected. And this function, when returning, it will return to, let's see, from the execution trace. So here we branch, we return to 2120. 2120 is inside, in fact, inside main function, and it's here right before calling radio test LED delay off. Okay, so this makes sense now. The firmware turns the LED on, then reads the current timer value, then does some sort of delay for 5 million ticks or so, and then turns it off. Let's check the source code as well to make sure our understanding is correct. So this is the main function. Similarly, we have these calls. We landed here. Tick start. It says tick start radio. Turn on LED for 5 seconds. 5 million ticks to show hardware starting. Alright. And here it passes 5 million. Now we have a good idea of how counter peripheral is supposed to work in nRF52, and we are ready to start modeling it. Before writing the timer peripheral, let's just copy and paste the code for a P0 GPIO peripheral because it is really simple. So the most notable part would be here. As you can see, if we receive a outset write to outset address, we go through the all bits in the value. Each bit is an indication of a pin number. If that bit is turned on, we put them into an array and print those bits as the bits set to high. And if it was a clear command, basically turning off those pin, we do this. Now let's go back to the timer. So remember, the timer had the block diagram showed these commands: start, stop, clear, count command as well. Let's first implement this command. So start command, it would be a good idea here to use a separate thread to keep the track of the counter value and actually do the sysdig, and then we can check if that thread is let's do this. Then we have a method to stop the timer. Now the flag is and then let's join the thread. Okay, so we start in this loop, we pick the value. That's nice. We have a separate function for tick and count because the clock has two modes. We want to use the relevant function for that. Then we measure the elapsed time, which is let's use a timer resolution, the smallest timer resolution. Resolution 1, and that would be timer resolution. Then we sleep. Otherwise, we continue the loop. Okay, and then here we exit the thread. Let's just copy paste the register names for the initializer. Yeah, so here it is. Okay, base address, we have the following task capture and CC register. We save the values of those CC registers inside this array. Our counter, which will be used both in counter mode and the timer mode. Thread and this one. Okay, we're ready to implement the read and write operations. If the address is being read was one of the CC registers, we need to read the relevant value from this array and put it and write it to the unicorn memory location. Okay, if address was between 0 address and address CC5, then we calculate the index of that array, which would be address minus divided by 4, and then the byte array is that index converted to byte array, and then we write it to Unicorn. That's ready for write. We have we need to handle those commands here. So if address was equal to tasks start, then we call self.start, and if address was equal to tasks stop, then we do stop. And finally, if you want to do the task capture command, because we have 5 registers here. Tasks capture 0 address and then we calculate the index again. And then we write it to the register array. Value of the current value of the counter, and in minions. Okay, that's good. And the finite is also at the get name. Before running the emulator, let's also increase the timeout value, because right now we are supposed to wait 5 seconds. Let's put this here, and then right. Okay, the timer is started. It should take roughly 5 seconds. Yep. So this is good. Our timer works, because at the end of the timer you see that the 8000 value is written to out clear, meaning that the LED is turned off. So we pass that point, and here our the GPIO peripheral actually announces this, that these GPIO pins were clear, 15. Good. And then we hit some error from invalid instruction error from Unicorn, which says this instruction, and again MRS family instruction here, cannot be handled by Unicorn. Let's investigate that address F1A. Yeah. So PrimeAsk register is a special purpose state register in ARM Cortex, and let's read about it. register. Mask register used for priority boosting, and usually this mask register is used to enable and disable interrupts. So setting this only has 1 bit actually here, all others are reserved. So if we set this to 1, it will disable interrupts globally, and clearing it, setting to 0, enables interrupts again. Most probably here the firmware attempts to disable these interrupts before starting the radio, setting some states, and then restores it here again at set primes. Since we are not really interested in this type of behavior, it would be safe to either just skip this single address instruction here, or just the whole MSR MRS read instruction. Let's do the latter. Add this to instructions to escape MRS, and then give it a try. Our timer starts, and we still have another one, MSR. Yeah, forgot to put the counterpart, the right column, save register instruction as well. And let's also stop the timer here. After MU start, timer starts, timer passed, and good. We have timeout. So to run it without instruction tracing to get okay, here is the delay for the timer. Good, and then let's see what happens after the delay. After the delay, the pin is cleared, those instructions, and we see that read and write events to new peripherals, the radio peripheral, RTC, real-time counter, and some interesting events related to radio. Okay, let's read the radio documentation and find out more about these registers, which helps us to model them correctly. The 2.4 GHz radio, here is the block diagram. As you can see, the radio has a DMA unit, which acts as a communication channel with the firmware. Once the firmware wants to send a packet, it places it in a pre-agreed location stored in packet pointer register and signals the radio to pick it up. Similarly, when the radio receives a packet, and processes it. It places the packet at the same location and raises an interrupt that should be handled by the firmware, which is expected to be handled by the firmware. We will get to that later when writing an interrupt controller for emulator. Next is about the structure of this in-memory packet. So packet configuration. So this is on air structure. We need the in-memory structure, which is documented here. Radio packets are stored in memory inside instances of radio packet data structure, as illustrated in this figure. So it starts with a field called S0, length S1, and the payload. And it says S7 length and S1 are optional. Okay. The size of S7, S0 length and S1 fields can be individually configured in PCNF0 register. Okay, important. If any of these fields are configured to be less than 8-bit length, the less than 7 bits of the fields are used. If S7, S0 length or S1 are specified with 0, these fields will be omitted in memory. Okay. Let's see what values or values is written to this register by the firmware. PCNF, it was PCNF0, I believe. Yeah. Okay, we have value 8 return to PCNF0, nothing, no more writes. PCNF0. Okay. Packet configuration register, and here is the illustration. Value 8 in binary notation would be 1000. So it will translate to this bit being 1. So this AA identifier actually tells the radio to set the length field, the bit length of the length field. So it would be that the length field will be 8 bits, 1 byte of length, and then 0 and S7, S1 according to this illustration would be 0, so they will be omitted. So the desired or specific radio packet format would be length immediately followed by the payload, and this is the in-memory format. Alright, let's move on to those. You notice those events registers. Let's run this. Okay. The write attempts start to the radio starts at 1C, 1A. C1, C1A, which is inside radio hardware RX receive start. So it basically sets these event registers to 0, and the sequences tells us that towards the end the firmware sets a RAM address, RAM location, as we expected, to packet pointer, and then writes 1 to task RxEN. Let's see, tasks RxEN. enable radio in receive mode. Okay, this makes sense. We also see many events. It suggests that the radio can raise interrupts in different stages of packet processing. For instance, when a packet is received, when the payload part received, which is this event, and when the whole packet is received, event end. Also, there should be some mechanism that the firmware indicates to the radio which events it is interested in, and this is done via int en set register, enabling interrupt for various events. As you can see here, for event ready, we will set this bit to 1, and similarly for other events. Let's see how the firmware writes to this register, which is int enable set. It writes value A, which in hex in binary notation would be 1010. So basically D would be set and B would be also set, meaning that the firmware is interested in receiving address event and end event. This makes sense because firmware would want to be notified when the packet is fully received. For some reason it is also interested in receiving the address when the transceiver is going through this part of the process, basically starting to do address match and before packet disassembly. Okay, in the next video we will create our radio peripheral according to these observation, and then we will also write an interrupt controller to simulate packet reception events just like the real hardware module. Until then, goodbye.